Welcome back to the Project BESS Deal Lab. In this lesson, we are going to build the cash flows that sit behind case 1 on this dashboard, the full tolling agreement for the 2-hour battery. You can see those cash flows reflected here in the cash flow waterfall and in the revenue sources chart. For now, all revenue is coming from this dark blue CTA bar, which is our capacity tolling agreement. Our goal in this session is to connect that story back to the inputs and then actually model the CTA revenue in the operations sheet. But before we get to the modeling part of this lesson, let's jump back to the information memorandum and focus on monetization pillar 1, contracted capacity revenue. For this lesson, we are only looking at the left column, the full toll 2-hour CTA case. Here we have a 2-hour BESS with 200 megawatt capacity at the point of interconnection and 400 megawatt hours of nameplate energy, backed by a straightforward capacity tolling agreement on 100% of the AC capacity. The contract duration is 20 years, starting at COD, which means the off-taker effectively rents the AC capacity of the battery for the full term. The payment basis is a fixed capacity payment of $9.5 per kilowatt AC per month, which is an industry standard unit for BESS capacity payments. This price is escalated at 2% per year as specified in the contract. There is no merchant overlay and no arbitrage in this base structure. It's a pure tolling agreement where the off-taker controls dispatch and pays for capacity. From a lender's perspective, this is the cleanest revenue structure we will model in this course. Cash flows are 100% contracted and fully indexed, so debt and equity see the same revenue profile in the base case. And sensitivities will be addressed later in the course, once the core model is complete. Now let's move into the inputs time independent sheet and see how these terms are translated into model inputs. Up in the revenue stream selection section, you can see that for case 1, the only revenue stream turned on is the capacity tolling agreement. All other revenue options are switched off. Under the CTA block, we set start after COD to 0 years, which means the contract begins at COD. And the contract term is set to 20 years, matching the asset life of the battery. The real CTA price, which is the price before inflation is applied, is entered as $9.5 per kilowatt AC per month. That's a contractual capacity payment. And the price escalation here points to a time series in the inputs time dependent sheet, where we have defined a simple 2% per annum escalation curve. In the information memorandum, it's also stated that plant unavailability is not compensated. Availability risk stays with the project, while curtailment events are compensated. In other words, if the asset is down due to technical issues causing unavailability, the off-taker doesn't pay. But if the system operator curtails the project for grid reasons, the CTA payment continues. In practice, lenders may overlay a more conservative availability assumption than equity investors, unless the long-term service agreement for the BESS provides a strong availability guarantee that aligns with the CTA requirements. Now that we've validated the inputs, let's go to the operations sheet and set up the actual CTA revenue calculation. If you're new to this Deal Lab series, I recommend starting with part 1, where you can download the model start file for free and build the full model alongside me. The link is in the video description below. Okay, now let's get to the modeling part, and we will start with our CTA flag. The CTA flag is essentially a simple on and off switch that allows us to enable or disable CTA revenue for the live case without having to touch any of the underlying formulas. And here we will start with a traditional if and function for dates and flags. And this flag is very similar to all of our other courses, so we will start with an AND statement. And first thing we will pick up is our start of period in K5. Anchor this to the row, so hit F4 2 times. And if the start of period in the column is greater or equal to our start period right here for our CTA, hit F4 2 3 times to anchor it to the column. And our second condition is that our end of period up here in K6, hit F4 2 times. is smaller or equal to our end date of our CTA term, hit F4 1, 2, 3 times. Then we want a flag, so a 1, otherwise 0. Close parentheses. So that's just to pick up the timeline. And last thing we'll multiply this with is also our on and off switch. So right here in cell G128, we can select whether this CTA is on or off. So let's multiply it also with this switch. Hit F4 1, 2, 3 times and hit enter. Now let's drag it over, Control R. And you can see we get 20 flags during operations. So our CTA is active for the full asset life. Now if you were to switch our CTA revenue off here in the inputs time independent sheet, let's see what happens. We turn this one off and you will notice the flag turns off. That's why we will multiply most of these formulas here with our flag to ensure that if we actually turn this revenue stream off, all these formulas aren't picked up here. Let's turn it back on. Then we can move on to our CTA price in real terms. This is very simple. So we pick up our price of 9.5 US dollar per kilowatt AC per month. Hit F4 1, 2, 3 times to anchor to the column. And we'll multiply this with our CTA flag. Hit F4 1, 2 times to anchor to the row. Drag it over, Control R. And you can see the price is only picked up while the CTA is active. Now, as you know, as per our information memorandum, we also get a 2% inflation on this real price. So this price here is before inflation is applied. And in row 125, we will actually consider inflation. So here we will pick up our real price, so the 9.5 times. And now we will use an X lookup. So type X lookup. Our lookup value is the drop-down menu that we have selected in our inputs time independent sheet. So hit F4 1, 2, 3 times for this one. Our lookup array is further up in the sheet, so let's scroll all the way up. And that is going to be our indexation list right here. So let's select all of these 6 inputs. And we will fully anchor them, so hit F4 once. And for our return array, we will select the corresponding index. So select those 6 cells here and hit F4 1, 2 times to anchor it only to our rows. If not found, we want a 0, 0, and the match mode is exact match, so also a 0. Search mode doesn't really matter, so close parentheses, hit enter, and let's drag this over to the right, Control R. And now you can see that our inflation kicks in and our actual CTA price starts inflating. And if you scroll back up to our inflation assumptions, you can see that the base year is in year 2025, which is why our price in 2026 is already slightly higher. Okay, now that we have our price, we also need to pull in our capacity, because unlike renewables plants, we in this case do not get paid for actual energy that we generate or deliver, but we get paid for our installed capacity. So what we'll have to do here is pick up our contracted proportion, which is in H128, hit F4 1, 2, 3 times. So the model has flexibility to actually say that only, say, a certain percentage of the battery is contracted, and the remainder could be sold differently, such as utilizing merchant arbitrage. And this contracted percentage we will multiply with our flag, our CTA flag, hit F4 1, 2 times. And then we actually have to pick up our contracted capacity, and now watch the unit here in kilowatt AC. So let's scroll up to our previous section that we've built in the previous lessons. And let's find where we have our kilowatt AC. And before any adjustments, that would be row 47, our gross power on an AC basis. And here in parentheses, it also states for US dollar per kilowatt month products. So that is the proper row. Hit F4 2 times, hit enter. Let's drag this one over, Control R. So before any adjustments, we have a constant 200,000 kilowatt AC installed, or 200 megawatt. And next we will model something that is often not even seen in BESS models, even in lender models, but it's highly important to include a nameplate adjustment also for capacity products, because what happens is that after degradation, we might actually breach our guaranteed capacity under our CTA. So what we'll do is use an if error statement, and we will scroll up. And in our previous lesson, we have determined our AC deliverable energy cap per cycle. So this is the actual AC energy that the battery is able to deliver in each specific period. And if we were to breach any of these periods here due to degradation, we could not apply 100% of the capacity under our CTA, which is why we need an adjustment factor in case we ever were to breach our minimum nameplate capacity. So we'll pick up K105, hit F4 2 times, and we will divide this by our point of interconnection nameplate AC energy per cycle. So this is the product that we guarantee, the 400 megawatt AC, the 400 megawatt hours on an AC basis. But if the battery cannot deliver the full 400 megawatt hours AC, then we need to adjust it accordingly. Hit F4 2 times as well. And if that's an error because we divide by 0, then we want it to 0. Otherwise, the other value will be picked up. And last thing we will do here again is multiply this with our CTA flag. Hit enter, and let's drag this over, Control R. And now let's do a little test and see what happens if we go to our augmentation inputs, and we will actually turn the augmentation off. So here right now we restore 15% above our AC nameplate energy once we are about to breach that minimum nameplate energy. And you can see we get a fail here because we have a nameplate breach. And what will happen in our operations sheet is that this nameplate adjustment here starts to decrease in accordance with the actual energy that the battery can deliver in these last years. So this is why it's so important to model this nameplate adjustment. So let's adjust this input back to 15%. Make sure that we always maintain our minimum nameplate capacity. And then we can model our capacity after nameplate adjustment, which is very simple. We multiply our contracted capacity before adjustments times our nameplate adjustment. Drag it over, Control R. And now we also have to model 2 additional potential adjustments, which is our availability adjustment and curtailment adjustment. And as previously mentioned, we do not get paid for unavailability events, which is why this adjustment here is applicable and turned on. But we will get paid if the system operator forces us to be curtailed. This is why this switch here is turned off. So let's actually implement that in our formulas. And first thing is we will pick up the capacity after the nameplate adjustment. So K130, and multiply this with an if statement. So if our switch here in G131 anchored to our column, so hit F4 3 times, equals 1, which it does. So on equals 1, off equals 0, comma, Then if that's the case, let's scroll up to our availability adjustment. And that is modeled in row 32. Then we will pick up row 32, hit F4 2 times. And if this switch were to be turned off in G131, then we want 100% instead of say 97. So that's why we just simply type a 1, close parentheses, hit enter. Let's drag this one over, Control R. And you will see that we will actually just get paid for 194,000 kilowatts, because after availability adjustment, we lose 3% of our capacity. And now let's do the same for our capacity after curtailment. And here we pick up our capacity after availability. So make sure you pick up row 131. And we will also multiply this with an if statement. And if the switch here is on, so 1, then we want a 1 minus our curtailment adjustment, which is in row 33, which is 1%. And that's the reason why we have to take 100% minus 1%, hit F4 2 times, close parentheses. And if that adjustment is off, then we want again 100%. So 1, close parentheses, hit enter. Let's drag this one over, Control R. Let's see what happens if you were to turn this adjustment on in our inputs time independent sheet. That's right here in row 90. So if we flip that switch on, then we would usually expect a reduction right here. So let's see what happens. Okay, here you see how important it is to get the anchoring right. We didn't anchor our switch properly. So let's always make sure we get the anchoring right. So hit F4 2, 3 times right here. Let's drag it back over, Control R. So that was a good test. And you can see now our actual capacity is indeed adjusted downward further in accordance with our 1% curtailment loss. So let's flip that switch back to off. And now we are almost done. So our applicable capacity for CTA revenue is going to be a simple linkage just for display purposes. That looks a little nicer. And now we can wrap this lesson up with actually modeling our CTA revenue. And this is going to be simply our applicable capacity times our CTA price on a nominal basis, so after inflation. And now let's make sure we get this right, because here this unit is in US dollars per kilowatt AC per month. And we are looking at a yearly model. So 1 year has 12 months. So what we'll have to do is we have to multiply by 12. Or in this case, there's a predefined name, which is months year. So months year is going to be a value of 12. But now we still have to do one further adjustment. So this price here is given in USD, while the CTA revenue is in thousands of USD. So we also have to divide this by 1,000. And it's best practice to name all of these values to avoid any errors. So we just type 1,000, hit enter. Let's drag this over, Control R. And you can see that in the first year, our CTA pays 22.5 million USD, which is increasing up to 32 million in our last year due to the inflation effects of the underlying price. Let's quickly jump into our text sheet so you can actually see these named inputs here. And we have 4 different constants right here, which is days per year is 365. We have named that cell as days year, then months year, 1,000, and a million. And that's how you set up a best practice model. All right, guys, this was it for this lesson. I hope you enjoyed it. And in our next lesson, we will tackle our resource adequacy contract. All right, see you there.